Okay, let's get started. So first, a few reminders. It's bouncing because it's today. So if you didn't sign up for this yet, you should panic and go over to Butler Hall and see if Jacob can squeeze you in. If not, once we get back from Labor Day, you still have that whole week of like the point level going down 10 points a day, and you can schedule it then.
And this Butler 101.
Is it 10?
It was 102.
102? Okay, yeah. And they've like subdivided some things over there, so there are new letters appended to things, but yeah. You'll see it, I'm sure. All right. Okay, so last time we were talking about linked list. We did a little bit of comparison between arrays and linked list and the trade-offs there in terms of the time that it takes to do certain things, the amount of space that it takes to do certain things. And so today we're going to continue on with linked list, and we'll start to implement a linked list. And that'll actually be part of your next programming challenge, which you won't get for at least another week here. But we'll build a linked list in class, and actually it will be everything you need for your challenge. You'll actually take stuff out of it that you'll add back during the challenge time. But we'll build this together in class as we go, and I'll also post that code for you once we're done with it so that you have it. We're starting today. We'll be doing it today and at least a little bit on Wednesday. So just to kind of refresh, we remember the main thing with an array is it's kind of this contiguous block of memory where we allocate these slots of different sizes and we put our items in there sequentially. We're able to index into it very quickly if we know the index of something. Whereas a linked list, we kind of have these little nodes and they just point to each other. And this has the advantage of we don't need to allocate the whole structure up front. We can just hook a new node in by changing these pointers, and that gives us an efficiency gain on some operations, not everything. So there is a trade-off here, and there are good uses for arrays, good uses for this linked list structure. And most importantly, from a linked list, from this basic linked list, what we want to do is kind of just get familiar with the idea of these linked structures in general. So we talked about some of those trade-offs between the array, between the linked list. Things like indexing into it, if you know exactly what item you want, what position it's at, obviously that's very fast in an array. Whereas things like adding or removing at the beginning with an array, you would have to shift everything in most implementations, whereas a linked list, you would not. The same with adding or removing at the end of the linked list, if the linked list is implemented in a way that it keeps a reference to the end. It's just a constant time lookup to do that. So we also briefly mentioned kind of this big O notation about worst case runtime. And that's a concept we'll move into probably a week from today, where we'll talk in more detail about this kind of notation and runtime and some worst case, average case, best case, and how those all play together. And we'll look at it. We'll start with the linked list, but then we'll do it on every data structure that we do this semester. But just to give you a little bit of intuition, in general, you see something like a big O of 1, that's a constant time. We're just saying it's pretty much negligible in terms of it doesn't matter the size of the structure that we have or the amount of data. It's always a fast, guaranteed operation. And you'll see some of these are order of n, which just means n, the number of elements in our data structure, is how we're approximating how long the worst case scenario is. And essentially we're saying something like, oh, well, for this operation, we would have to actually look at each element in this structure. And so that would take us in, accessing steps. Okay, so today I've just called linked list 2. This can go on forever. Hopefully it will not go past 3. All right. Oh, before I forget, I put your quizzes, I scanned them and put them on Canvas. If you took a quiz and you have like a 0 or something, please let me know in case like it got sucked into the scanner and I just didn't, see it. But I think everybody, I think the number I counted is the number of pages that it scanned. So, but always let me know if it shows up with the wrong grade or something, and I'll hunt it down. And you should be able to see your scanned copy of your quiz on that grading canvas. Okay, so linked list, the general structure and the kind of the operation that we used as our main example was if we have this linked list with these nodes, and in our case, we're just going to say that in our linked list, our data is an integer. Your data could be anything. It's just easy to start with an integer here, but it can be anything we want. And so in this linked list, we have each node has the data, the integer, and then it has a pointer to the next node. And that's all that we have here. So if we wanted to add the data 4 to this list, we kind of went through this, where we would have to first create a node with 4 in it that's not pointing anywhere. Then we would have to, in our case, find the insertion point, because if you remember with this example, we wanted this to stay sorted. That was just an arbitrary requirement. It's not like a linked list requirement or anything, it's just what we're doing. So we start at the front of the list, because that's what we have access to, and then we start to see, okay, is that, less than 4, is it greater than 4? Where does 4 fit? We navigate down until we find 12 is too far, so obviously this is where 4 fits. So now that we've located that point, we can take the next pointer from the node that has 2 in it, have it point at our new node 4, and have our new node point where 2 was pointing. And so we just rejoin that together, and it's all connected again. And so apart from finding that place to put it, it's a pretty constant operation. There are just, these pointers that you change, and it's always that number of pointers. So now I want to introduce a different linked list. This is called a doubly linked list. And as you might imagine, we've just added, we had next where we were pointing to the next one. Now we've added a previous field, so we're pointing backwards as well. So now we've got 2 links all the way down this list. And so this gives us the ability to come in from either side, essentially. So you can come from this side or that side and navigate through the list. This has some advantages. One thing that you should think about, a linked list it seems more efficient, especially in terms of space, because you're thinking about like an array where you allocate this set amount of space, right? But we have to allocate these pointers for each of these nodes, right? And so in our case, like an integer, the size of an integer here is probably the same as the size of each of these pointers. So it's like 3 things that we've got here. So there is a trade-off, like on a practical level, when you're doing this, especially with kind of these basic things. Now, if this were not an integer, if it were quite large in comparison to these pointers, that would be a different story. But also, this could be a pointer, right? So we could just point to something else, and we could do that with an array too. So it's not always kind of just like, a clear thing that this is the better data structure.
Do you think linked lists are easier to write than arrays?
Than actually writing an array. It's not, okay, so if you wanted to actually write an array, right, so the language has an array built into it in most cases, but what you can do if you want to do that on your own is you have to just say in C or C++, you've got malloc that will just give you a chunk of memory. And so you would write code that would take care of getting that memory, dividing it up, doing the indexing, all of that. And it would, to make it perform as well as what's built in, it would be hard. Because it, in a lot of cases, comes down to very optimized instructions once it gets compiled. So a linked list, I think, is a better one to implement from a high level. So.
And that's what we implement.
Yeah, we're going to implement that. Yeah. Yeah, an array I think would be a lot harder for us to implement, honestly.
Oh, okay, so
Yeah.
linked lists are easier.
I mean, it depends. It depends on how you feel about it. All right, so the linked list, the doubly linked list, we've just got the pointers forwards and backwards, and then I'm going to get rid of those because it's taking up too much room on my slides. So here, we've just got 4 elements now. This is just an example, arbitrary example. I've just got integers in here. Again, it could be anything. So for the linked list itself, we keep track of 2 things, and we're going to call it head and tail. You could call it beginning and end, you could call it front and back, whatever you want. The challenge code that you'll use for challenge 1 that deals with linked list, it calls it head and tail, and it helps the TAs out if I use that same naming convention. So we'll go with that here, but just know that these are arbitrary names. Really, you just want something that means the front and the back of the list. And so if you hear me mess up and say some other term, you know. Okay. So initially, we had these dangling pointers here that weren't pointing at anything because there's nothing before them or after them, right? And so what we'll have them point at when there's nothing to point at is what we'll call null, which is just nothing. And most languages have some concept of null or nil or something like that, and it usually is mapped to some kind of constant value that you don't ever have to look at. In C++, we'll use null PTR as the keyword, which just means a null pointer, and it just means it's mapped to nothing. And so we'll use that when we initialize things, just so we don't have it pointing somewhere random, and we know that we haven't pointed it anywhere yet. And that's what we'll do when we create a node. So we're going to go through building this data structure of a linked list, of a doubly linked list. And these are the different functions that we're going to add to our doubly linked list. These aren't the only functions that you could put on this list. These are the ones that will be part of your challenge, and it's a good subset of things that you would want to do with this structure. So kind of just to go through them so that you get an idea of what kind of manipulations happen here. So the first one, and this is kind of the order in which we'll go through them as we implement it, but is basically just append to the end of the list. So just add to the end of it like you would any other list or array. Just put a new element at the end. If it's empty, it becomes the only element. The second one is to add to the front of the list. So that's pretty basic, and that's kind of the first place where you see that advantage over arrays, right? You don't have to shift because you can just stick it in the front. Third one is just basically a print function just to display the whole contents of the list, which is great when you're debugging and you're building the list. You'll need that. Quick question, how long does it take to display every element in the list? Linear. So if we were talking about the O1 or N, yeah, N. So that's something to think about, right? Because we got to go through each of these N elements. And that's give you a little bit of intuition there about each of these operations. Again, that's pretty good, and it's great for us because we're doing small things. So the next one is search. And so in this one, what you're going to do is you'll pass a parameter. In the case of this code, we're going to search by value. So we're going to store integers. And the search will simply look to see if that integer exists in the list. And as soon as it finds it, it will return true. If it can't find it, it'll return false. You could think of a lot of other things you could do here. You could return the actual node. You could return, the count of how many nodes you went down to get to it. And then, of course, you could handle the case where there's more than one of that same data value. But we'll keep it simple. We're just going to say, is it in here or not? Remove. So we'll also do our remove by value. So we'll just be passing in the integer. And if that integer is in the list, we want to remove the node that it's in. And again, you could do that different ways too. We have tail display, which is the same as display, but from the other side. So you can do that in reverse. And then tail remove, which is just to take a value off of the end of the list. So coming in from the other side on the doubly linked list to do that. So let's start with thinking about this node structure. So this is each element of the list, right? We're going to do this with classes in C++. So we'll be making, our first class will be a node, or a list node, if you want to think of it that way. But that structure will have just three things in it. Okay? So it will have our data. In our case, we're just going to make it an integer. You can make it anything that you like. And it'll have 2 pointers. And these pointers will be to other nodes. So same structure. And one will be next, and one will be prev. So one pointing forward, one pointing backwards. So to put it into C++, this is the basic way that we can make a node class. It's very simple. In our case, we're just going to make all of these fields public, so anybody, any code can change them or access them. We're not worried about anything like that right now. And we'll have our data, we have our next, and we have our prev. But there are some things that we should remember to do. So in C++, I think it's just a good, and probably in any language, when you declare a variable, you should initialize it to some known value that makes sense for you. Usually it's like the 0 value or null or whatever means there's nothing there. So we want to be sure to do that with these nodes because when we allocate those pointers initially, it could be anything in there. It could be pointing to any memory address. And so this is kind of shorthand within C++ that lets us set these things just in this single line quickly, these defaults. So these are both constructors for the node class. One of them doesn't take any parameters. So if we were to just create it and not give it a data value, it would just set it to 0 for the data value by default. And we're just passing it in like that. This is just a shortcut notation within C++. And for each of the pointers, next and prev, we're passing the null pointer. And null pointer is a keyword. It's global. It's everywhere in C++. It just means we're not pointing at anything. So we've got one constructor that does that with no data coming in. And then we've got another constructor that takes in an integer value if you pass it and goes ahead and this wonderful statement, data will save whatever integer value you pass to the data field in here. Same thing. No semicolon. Weird, huh?
Is this supposed to be a semicolon, right?
No, it works without the semicolon.
Okay.
Yeah. Interesting. We won't cover details of C++ and wonderful things like that in here, but yeah, there's all kinds of fun stuff that comes along with a big language. Okay, so let's think about our list, our example that we have. We've got our 4 elements, we've got the head, and we've got the tail. They're all connected in this example here. And so we need a structure to represent the list itself. So the list itself really only has these 2 pointers, right? It just knows about the first element in the list and the last element in the list. So that's all we need for our linked list structure. And then from there, every node links to the next or the previous, so they take care of that. So it's also a very simple class initially here of linked list, where we're gonna go ahead and make these private variables within our class, and that's probably good practice. Again, it doesn't really matter here, but we've got the head and tail element, and then for our public functions here, we've got a constructor for linked list, so we can make a linked list object. And just like we did with that shorthand notation on the others, we've said, okay, by default, there's nothing in here, point to null, and so if there's nothing in here, well, the end is null too. And so we've set those. Now, what's important that we have, and this is somewhat C++ specific, C specific, we've got to manage our memory a little bit. So we need this is a destructor function, so the opposite of the constructor. And this is going to be called automatically whenever we're done with this object, whenever the runtime environment knows that we're done with it. It's going to call this function. And within this function, we need to be sure that any memory that we took in when we made this list, we let go. Otherwise, get the memory leak, and we just start saving memory that nobody else can take. So that's going to be an important part of this whole process of building the linked list, and it'll be, yeah?
This might not be the right question
Ah,
to
okay.
ask, but did we not need one for the node class?
So for the node class, we don't necessarily need one, depending on how you implement it. So because we can do those operations Okay, to answer your question, we should have one. Right, we should always have one. The right thing to do is to have one. But because we're handling everything, kind of linked list is like the high-level structure, we can reach in and take care of those node elements one at a time if we'd like. But yeah, I mean, a valid approach is to take and use the destructor of the node class too. And we'll see a little bit of when you need it, like definitely when you have to have this destructor and when you don't, and it has to do with the way we like create these variables. So you remember like we created one that was a pointer and used the keyword new, and that was different than when we didn't use the keyword new. That comes back with this. And so when you create using new, you always have to have this destructor. Otherwise you don't necessarily because the compiler can take care of it. All right. So then once we have our constructor destructor, we're going to start to add those methods that we listed on the table earlier. I'm going to start with the append method because probably want to put some data into this thing to start with. So let's go ahead and just set up a basic structure for this in VS Code. All right. So I'm going to just create a couple of new files. The first one I'm going to create is linked list.h header file, and I'm going to turn Copilot off. All right. The second one that I'm going to create is a linked list.cpp, where we'll put our implementation. And then third, I'm going to create just a test linked list.cpp, which it doesn't matter what you call that. Now, I'm not making a separate file for the node class just because it's so small. I'm just going to put it in the linked list header file, which you can do. Maybe not the best practice if you're dealing with huge things. Sometimes it makes sense. In this case, I think it's easier to just have it there because it's so small. So let's go ahead and start with the header file for linked list. If you remember this preprocessor directive that we do, which is just to tell the compiler when it comes through in the linker to not include something twice. So here I'm saying if not defined, I'm going to define. So if not defined in this variable name, which I'm just going to call linked list _h, it's totally up to you what you call it. You just want something unique per file here. So if it's not defined, then I'm going to define it. That. And then I'm going to go ahead and go down to the bottom and do an end if. And so all that means is everything in between here. Oh, that's small, guys. I'm sorry. There we go. So everything in between here is conditional based on if this has been defined at a preprocessor level. So this happens before things get compiled. And it's just something to make sure we only include it once. Okay, so let's go ahead and start with that node class just for each element that's in the linked list.
So will we put like integer main
Mm-hmm.
and then the apostrophe, like the brackets?
Mm-hmm.
So the end if will go under the brackets?
So usually wherever your main is, you don't need this because you're not like making a new library or class or anything there. It won't be included in anything else. And you can only have one main function when you compile a set of files. So it can be outside of it. But usually you won't even have that in the file that is where you're running things from. This is just usually in like the class definitions. And the reason is that like you might use a linked list in a bunch of different files. So if you imagine like you had a bunch of different classes and maybe all of them needed a linked list, they would all include linked list. But the compiler only needs to compile that once. And so this is just the kind of hacky way, but standard way that we do that in C++, is just to do these definitions, and that way the compiler knows, just ignore it if I've already done it. So. Yeah. So, I mean, most of, like Python, Java, C#, kind of just the variety of, I guess, modern languages that came after C++, they handle this for you. You import something, you include something, whatever. It takes care of this automatically. Here, we just kind of get to see it done for us. So, all right, let's make the class for Node. I'm just going to call it Node. And we'll remember that we need a semicolon after the class, otherwise everything is horrible. Okay. So I'm going to start with just the public functions and members of the class. In our case, we just have the data, which we said was an integer. We have the 2 pointers, and these are going to be pointers to nodes. So their type will be of a node and the star for pointer. So we'll do next, and so another thing I'd just like to remind you, when you'll see that I'll always put the star with the type here, because I think that is helpful to remember that that's a pointer type that we're using. It doesn't have to be up against the type. You may see in other code that it is just in between. There may be like a space like that. Things could be really awful like that. I find that confusing because later this kind of means something else. So at this point, we're really just saying we want 2 pointers of the type node. And so grouping these together kind of keeps it clean and easy to think about.
So
Yes.
this class would be written above our main, but it could be written under the user namespace std.
Yes, so we could put this into the namespace std if we wanted to use something from std. Yeah, the namespaces are not intertwined with the classes and their names. You could still have conflicts and stuff, but yeah, we could use this with namespace using std. Yeah.
So yeah, I could write it under that, but write it above my main.
You could. We're going to do it in separate files just to keep things organized a bit. You could do this all in one file, yeah.
Mine, because on C++, I don't make different files.
Oh, okay, we got to make different files. You got to try that because it will make your life better, I promise. And I'll show you how to make the compiler not get mad at you about it. But yeah, you can put it all in one file. You can put it all in one line if you want. But it's just for your convenience. Probably like if you're doing work and it's not just you, other people will appreciate it if they have to read your code, that we kind of organize it in this way. Although I think that's like a software engineering topic really, so I don't know, we should just kind of have a free-for-all in here. But your TA does have to read it, so that's probably the driving force. So I'll split it into files, and I'll show you how to do it with these files. But yeah, it does work with just one file. Okay, so we've got our data, our 2 pointers, next in prev. And so now, if you remember from the slides, we need our constructors for the node class. And so I'm going to do those, which they're just the name of the class itself. And in this case, I want one that's just the default. I'm not giving it anything. I'm just going to say I'm creating a node. I'm not passing any data. And I'm going to use this shorthand notation that lets me set these member variables that we just declared all kind of quickly here. We could spell this out in more detail if we wanted, but again, you'll see with things like this where it's simple that it'll be done like this because it's a quicker way to do it. I'm going to make this just a little bit bigger and see if I can squeeze it. Are you guys able to see this? Is this visible-ish? Okay. Try to keep it up here too. All right. Okay, so we're declaring our default constructor here. Data, we're setting it to 0 because we didn't pass anything in. Next, we want that to be null pointer, right? So we'll use the keyword null pointer. And then we'll do the same for the previous field. Oh. Autocomplete has decided to join. There we go. Okay. So now I can move a little bit faster. And then we're going to do just opening and closing curly braces here. Don't need a semicolon. I'll let you investigate that on your own. I don't really remember, so. Okay, so let's write a second constructor here. And this one will give a data value in. So like when we create the node, we can say, okay, I want to create a node for the number 4 or whatever. So it'll be the same, but in this case, we will take in an integer. I'm going to call it data because that's what it's called in the challenge code. And that means we will have to say data data, but that's okay. We'll be fine. And then we'll do the same thing for the next, which will be a null and prev. Oops. Null as well. And then, of course, we'll do our curly braces here. Okay. So I'm going to just have these two to start with. We'll add a third one later in this process that lets us specify these pointers, but right now we don't really ever need to do that. So, okay, so that is just our node class outlined here, and it's in the linked list header file. You could break it out if you'd like. It's really just a preference, but this is as big as it gets. So it fits kind of nicely here. Okay, so let's see. Now let's jump over to the linked list itself, the C++ file implementation. So here we want to do the same kind of thing. So we're going to, actually, I don't want to do this in the C++ file, sorry. We need to do the headers first, right? So, well, let's do them right here because this is linked list header. So we have the node up top, just extra here. Now let's do the linked list part of it. Sorry. All right.
With this part, it's still above the main.
So, yeah, all of this is nowhere near the main. So this on its own, when we're done with it, like you can't run it until we write a main. And we can write the main kind of wherever we want.
So none of what we write today is in the main?
No, none of it's in main, yeah. Okay, so I'm going to do the linked list class just right below this node class. And so we'll declare the class. Remember the semicolon at the end. So let's do the private members of the class. So we just do private colon, and then we're going to list out the things that we want to be in the private scope. And so in our case, we have a pointer to a node that is the front of the list, and we're going to call that head. So, and then we have a pointer to the back of the list that's tail. Okay. And those are the only private fields that we want in here. Okay, so now our public fields. Oh, and also, I will post this code, so if you do better just watching me and you don't want to type, that's fine, but if you do better coding, keep coding, whatever you want to do. Okay, so public fields, we're going to need constructor and destructor here for the linked list class. So the constructor, same name as the class, right? So linked list, let's do one that doesn't take any parameters. And we can use that notation that we learned with node, because at first, head and tail have nothing to point to. There's nothing in the list. There are no nodes. It's just nothing. So we'll do this, and we'll say head, and we'll make that null pointer. And then tail, which we will also make a null pointer. And we'll do this. Right. And then we're also going to need a destructor for this. And so that's just this tilde symbol, and linked list, same name as the class, just like that. And that one I'm just going to leave just like that. So these are just the headers, no implementation, except here where the implementation fits in, a little bit of space. So we go ahead and put it.
I'm looking for that squiggly line on my keyboard.
Okay, so under escape, Yeah, yeah.
Why
Mhm.
didn't we do a destructor for the node class?
So the way that we're using it at first, we don't need a destructor. I believe by the end of this process we'll add one, but we're gonna see, I'm gonna show a little bit of what happens when we don't have the destructor done right first, and then we'll come back and put the destructor in it. But in general, you should put a destructor always, even if it's empty. It's just kind of good practice in case because usually you're writing something that develops further, and then yeah, maybe you have something to clean up now that you didn't have before, so it's nice to have it. Yeah, it's a good question. We will add it before we're done. Okay, so for our first step, we're going to do that append method to put something into this linked list. So I'm going to just add the header for that here in the public section. So that's a void method, and we're going to name it append. And for appending, we'll just take in the integer value that we want to append. So we could choose to abstract this a different way. We could say, oh, you need to append a node, like you need to make the node before you give it to me. Because we're just dealing with some simple stuff here, it's kind of easier to just let this take the integer, and we'll handle making the node in this implementation. Okay, and so all this does is it adds a new node to the end of the list. Okay. Okay, so I think that's pretty good for right now for this header file that has both linked list and node in it. So now I'm going to jump over to actually using this. So I'll start without doing anything, any implementation. Let's just kind of set up our test file. And it's kind of a good thing to do when you start writing any of the data structures we go over and you need to implement. I think it's a good pattern to start with just the very basics of the data structure, no implementation, it doesn't work yet. Go ahead and set up your test file and make sure it runs, it can include things, even though they don't do anything yet, just to get that framework, because you'll be wanting to compile and run it a lot as you build it to make sure it works. So here we're in a file that I've called testll.cpp. You can name it anything you want. This is where we're going to put our main method in this file. So because we're going to be printing things, I'm going to include IOStream, and I'm going to include our linked list header file that we just wrote, which contains both node and linked list in our case. And for convenience, we will just use the full namespace std here. And let's do our main method. It's integer main return 0. That seems like it probably will work. I'm just going to put a print statement here. Okay. So let's see that. See if this all compiles fine. So again, the structure here is just a folder with these 3 files in it. So I'm going to use the terminal to compile this. If your editor is set up to handle this and link everything, that's fine. Probably easier, but this is kind of the simplest way to do this. And since we're only dealing with a couple files, it's easy enough to do this just to remember. So I'm going to use G++ as my compiler here. You can use whatever C++ compiler you'd like. The first thing that I'm going to give it is my test file that has my main method in it. And then I'm also going to supply my linked list .cpp file. And I will, actually, we won't give it an output name. We'll use the default. So if you don't give an output name, you run that. What it will give you, I guess I should have shown you what's in that directory first. The output that it generates is a.out, which you probably are familiar with. And so I'll just let it make that default. But if we wanted a name, we could specify it. So it's compiled it as a.out. So to run that, /a.out, run it. And there's our print statement. So we've done hello world, that's great. But more importantly, we've included these things, right? And nothing's gone wrong. So we're kind of working. Yes?
And the other one, what was it at the top that we had to include? So like, if we don't include that, it was not in the.
It's if in def, so if not defined is what it stands for. And then under it is defined. And then at the very end, it's end if.
And if we don't include that, it won't run.
So in this case, it would run. I think. I'm pretty sure. Anybody want to place bets on it? Or?
I mean, I ran it. They ran. I
Well,
was seeing if that was.
let's see. Yeah, it's okay. See, it's fine. It's fine because we've only included that linked list file in one thing, right? So that's great. If that's all we ever do, it won't be a problem. But usually it's not, and so it's just it's a good habit to always do it, regardless. But yeah, and I think honestly for linked lists, we wouldn't need it at all. That won't be the case for other data structures that we work on. Okay. I'm going to go back to my test code here, and I'm just going to write my first test method. And you can do this however you want. I like to just write functions that do different things when I'm building it. So like in this case, I'm going to write a test method that's just for appending elements to the list and displaying the list. So I'm going to do it up here above main, and I'm going to name it test, append, and display. And that's perhaps maybe some psychological childhood trauma or something. I like long variable names that are very descriptive. It can be really annoying at times. I totally understand that it's easier to just name it like, test one or something. I'll usually use a longer descriptive name on most things, just because otherwise it takes too long to come back to it and figure out what's going on. But you call this anything. And so in this method, what we're going to do is we're going to append, let's say, like some test data to the list, and we'll print it from the list. And we'll use the methods that we're going to write. So to start with, I'm going to say, okay, well, and we should call that, right? So from main, we're going to call that method test, append, and display. And these are, I'm not like passing anything, it's just a shortcut, just to kind of contain the code. So the first thing we could do here is maybe make a linked list, right? The object itself. So let me do that. I'm just going to say linked list, and I'll just say list like this, okay? So you remember this is one way to create an object, right? It's just to declare it. So let's take that. Let's go over here, and let's just see if we're still compiling and running. Oh no, we're not, right? So that's kind of a problem. Now, if we were to instead, let's get rid of that for a second. Will it be any different? Oh, but why? So the first one, the compiler's managing memory for us, remember? So it managed it. It said, okay, I'm done with linked list. Can we destroy it now? Let me call the destructor. Well, guess who hasn't written a destructor yet? So that's where the error comes from. When we do it this way, we're saying, oh, compiler, don't worry about, managing that. And we didn't call a destructor, so it's fine. The memory's just out there. Yes?
So why didn't we have to do a destructor this time? I don't really understand completely.
Yeah, no, it's a weird thing, and this is C++ specific. So what happens when we use the keyword new and we assign this to a pointer, the compiler no longer manages that object. And so like, when we come through main here, right, we say, okay, main, everything's empty, you know, we've got some memory. We print out this thing that we have. We call this function. This function creates this list. Then this function's done. Well, with the compilers in charge, the compiler's like, well, the function's done. They don't need linked list anymore. Throw it away. Call a destructor. We're done. Clean up. That's when you don't use new, you let the compiler manage it. And that's fine. There are plenty of circumstances where that makes the most sense. If, however, you don't want the compiler to manage it, and you want to do things that will go in and out of scope. So this is a simple case because it's just one function here, it's the scope. But when you start building the classes and bigger data structures, it will come to a point where the compiler can't take care of it for you. And so you'll have to use this approach here, which then does require a destructor. Or doesn't, I'm sorry, requires you to call the destructor rather than the compiler doing it automatically. So yeah, it's an interesting feature of the language and kind of how it's evolved.
So, like, with it being such a small segment of code, we don't have to call a destructor, is what you're saying?
It's kind of, essentially, in one case, the compiler, when it compiles the code, it puts the destructor call in there for you automatically. It doesn't tell you about it, it just does it. And that can be great, but when we don't want it, we'll use the other notation and it won't do that. In general, we're always going to use the second notation in this class. And this, again, is something that's language specific. So, you know, it's C++, other languages, this is not the case. They have their own quirks and features. But it's just something that I kind of want to remind you of because it'll be a weird error when it happens and you'll be like, it looks right, but...
Yeah, so it didn't run this time because the compiler called the destructor before we were done using it?
It called the destructor and we haven't put anything in our C++ file, right? We've only made the header for the destructor. And so there's no implementation of it. And that's what it's trying to yell at us about. Yeah. Okay. I think this is a good place to stop. You guys have a good long weekend, and I will see you on Wednesday. Yes.